Hello everyone, in this lecture we will try to generalize the closed form solution to the Cauchy equation given as this additive form equation, in the sense that we are extending our result from the set of a function defined on the set of reals to the reals, but for this to give us a continuous function results, we will have to make this additional assumption here. So that's important. This is a new addition. That condition here will ensure that our function is actually an increasing function and have the nice properties that we need to invoke the squeezing theorem or the sandwich theorem in calculus. So let's go ahead and start with our proof. We already know from a previous lecture that, so let me solve it in steps again. We already know that f of x, the solution to the Cauchy equation, is simply f of 1 times x for x in our rationals, and we know it from a previous video. In the second step, let's prove that our function is actually an increasing function. For x greater than or equal to y, notice that x minus y would be greater than or equal to 0. As a result, f of x, which can be rewritten as x minus y plus y, so the y's will simply cancel and you will get this expression, our original expression, is equal to invoking our definition, f of x minus y plus f of y. But then observe that x minus y is greater than or equal to 0, and now given our condition we know that the whole thing is greater than or equal to 0, suggesting that this expression is greater than or equal to f of y. So therefore we have just showed that whenever x is greater than or equal to y, f of x is greater than or equal to f of y, suggesting therefore that f is actually an increasing, monotonically increasing function. Now in the final step we will have to extend our result from the set of rationals to reals. So for x defined in reals, by using a very well-known property, the density of rational numbers, we know that there exist sequences Pn and Qn in rationals. So these are sequences made up of rational numbers, such that Pn is an increasing sequence and it's in the limit it approaches x, whereas Qn is a decreasing function and in the limit it approaches x, but by decreasing, in a decreasing fashion, such that obviously Pn and Qn, we defined it as an increasing and decreasing sequences, such that Pn is less than or equal to x, less than or equal to Qn. We can always find such sequences that will approximate to any given real number. So from the second step, by 2, we know that, well, check this out. So Pn times f of 1 is simply equal to, from the very first step we established data, f of Pn times 1, or simply f of Pn, but that is less than or equal to f of x, again by the second step, because if Pn is less than or equal to x, it suggests that f of Pn is less than or equal to f of x, but in a similar way that's less than or equal to f of Qn, which can further rewritten as Qn times f of 1. Now that's when I will go ahead and apply these the well-known sandwich theorem. When I take the limit of both sides, so the limit on the left hand side will approach, Pn approaches to x obviously, and f of 1, so it is just simply x times f of 1. The limit of the upper bound as well, so we just realize that the upper bound will approximate to, so Qn approximates to x, it decreases to x, and we continue to multiply it by f of 1. So therefore, by the squeezing theorem, the limit of f of x will also approach, because it is squeezed between these two entities, in the limit f of x will also approach x times f of 1 as a result. So therefore we are able to extend the domain and range of our functions and still able to find the solution in the following form, to the following result, where notice that our domain for x is all real numbers. Now I would like to make a couple of notes here. So first of all, notice that this condition here given in the problem ensures that our function f is increasing. In fact, this extra condition can be replaced with f being continuous at 0, or f being monotone, or similar expressions, and those type of regularity conditions will ensure that our solution will still hold and it will satisfy this this condition, this Cauchy equation. But we definitely need a regularity condition like this. Without the existence of a regularity condition like this, it turns out that the solutions can be abundant. You can have some absurd looking discontinuous functions which also satisfy this equation, which is kind of not in our interests. So adding this condition here, this regularity condition, helps us obtain a beautiful result like that one here. So that solves our problem. Hope to see you in our next video.